All right, so welcome back. We are going to continue on today with with a discussion on quantifiers, which is another way to say first order logic. Now, again, if you've never heard of these topics, it's okay. We're going to continue from kind of the basics and work our way up. What you do know, what you should probably know by this point, is all the rules pertaining to logic, the basic connectives for logic. So the and operation, the or operation, the implication, the biconditional, as well as the negation. So know that those are the connectives for the logic, for logic that we've talked about so far. But now we want to go one step higher. We want to go to the next level. So at this point, really the only thing we know is how to represent one statement that is true or false, and we call this a proposition or a statement. And we said whenever we have this, we assign it to be a variable, either p or q, and then we have a value associated, either a zero or a one, which is representing true or false. So can we go a little bit further with that? So what we want to do in this section is talk about quantified logic. So what quantified logic means is that we have a bunch of statements that actually work together in a whole universe. Okay, so it'll make a lot more sense once we get going on this section. But just remember that's exactly what I said. So, what is a type of quantifier? Well, a type of quantifier is we want to be able to make a true or false statement, not only on one statement, but on a bunch of statements. Okay, so not only on one statement, but a bunch of statements. So, let me just give you a few examples here. Earlier, when we were describing the definition of a proposition, I gave you a few examples. And I said at the time that this particular proposition, something like x is an integer, is not a proposition because we don't know what x is. So, in theory, x is I guess x would be like a variable, which we don't know what it is. But now we want to be able to add a little bit more information to x. We want to be able to define what x is. So, for example, I can have a statement that says something like x is greater than 3. Okay, so if I say x is greater than 3, now again, this comes pretty close to being a proposition, with the only exception that I don't know what x is. So this is what we call an open statement. This is an example of an open statement. And an open statement means that I have a variable, which I don't know for now. But if I have the value of this variable, then I can make a decision on whether it's true or false. So typically, an open statement will be labeled as a functional statement. And what we do is we have a function name. So let's call it P. We'll call it P in this case. So P of X means that I have a function depends on X, that depends on X. Okay. Now, if I just give you P of X, can you tell me whether this thing is true or false? Probably not, right? Because you don't know what x is. So there are two parts of this statement. So one is called the variable. So this x is called the variable, and then the rest of this statement is called the predicate. So oftentimes you will hear people say that this is predicate logic or first order logic. So that's what they mean. So we're talking about a predicate or a propositional function. Okay, so propositional function is another way that people would describe an open statement. Okay, so what do we need in addition to this to be able to signify that there is a true or false value? Well, there's a second thing, which is called the universe or the universe of discourse. Okay, the universe of discourse is an open statement which has of an open statement are the values that can be substituted into the variables. So if I have a p of x, the universe means what values can x be? Okay, what values can x be? So in this case, let's say the universe is integers. Oh, sorry, integer universe of the variable x is integers. Okay, whole numbers. So now what you're told is that the x can take on whole number values. Okay, 0, 1, -1, 2, -2, 3, -3, and so on. So they can take on any of those values. Okay, now at this point, do we have enough to determine whether this statement is true or false? This p of x is true or false? The answer is no, not yet. We're getting closer. We know that x is an integer, but which integer is it? right? Are we making a statement about one integer? Are we making a statement about a bunch of integers? I don't know. I don't know what x is at this point. So we're getting closer. So the first part is we need an open statement. I'll actually label these number one and number two. So this is our part one. We need an open statement. Part two, we need a universe. And then part three, we need to somehow quantify this. Okay, we need to somehow quantify this statement. So what do I mean by quantify? Well, I need to tell you exactly what x is. So one of the simplest ways to do this is that I can simply plug in one of the values into x. So I can plug in the number 2. Okay. Now, if I say p of 2, then you could probably guess that this statement is saying 2 is greater than 3. And you can see that this value is going to be false. It's a false value because 2 is not greater than 3. On the other hand, I can plug in a 4. I can say p of 4, and you can conclude that this is a true statement, right? So this has the value 1. Okay, so this is what we can do to quantify the statement by just plugging in one of the objects in our universe. But that's not that great, right? Because if you think about it, if I wanted to make the statement 2 is greater than 3, then why don't I just write it out? Why don't I just write it out as a proposition? That's what we did in the previous section, in the previous chapter. But instead, what we want to do is add a little bit more quantification to it. Okay. But for now, I want you to remember that one of the ways to quantify a statement is simply to plug in an object from the universe. Okay. But that's quite simple. So we want to add a little bit more to this. But just as an aside, um, the whenever we define open statements, we can define them on more than one variable as well. So for example, I can make an open statement that's like p of x, y, z, and this could be a statement that is x plus y is equal to z. So again, if I have the universe of integers for the variables x, y, and z, so if these are all integers, okay, so if x, y, and z are all integers, I can say something like p of 2, 3, 5 is a true statement, whereas p of 1, 2, 9 is a false statement. So we can have as many variables as we want in the predicate. Just as a side note, we're going to come back to this fact a little bit later in today's class or in today's in this section. But let's move on. So what else can we say about quantifiers? Well, there's basically two types of quantifications, or two main types of quantifications that I want to talk about. Of course, putting aside the fact that I can simply plug in a value into the x and get a true or false value, I can also do a universal quantification, and I can also do an existential quantification. So universal, which I'll explain in the next few slides here, means everything, means every, okay? Whereas existential means some, okay? So every means everything, and some means at least one, okay? Some means at least one. So there are these two ways in order to quantify a particular open statement to make it have a true or false value. Okay, so I think there's enough explanation there. Let's move on with an example. Probably the best way to see how this works is through an example. So, what if I told you that every Macam 101 student loves pizza? Okay, now this is a statement. Every Macam 101 student loves pizza. So, of course, you can again you can verify here that this either has a true or false value. Okay, so it's either true or it's false. So this is going to evaluate to either 0 or 1. But this is not only just one statement. So let's break it down and take a look at exactly what this statement is saying. So the first thing we need, so remember, number one is an open statement. So the open statement is a predicate. So what is this statement talking about? Well, this statement is talking about X loves pizza. Okay, somebody loves pizza. So I'm going to label this as P of X. So P of X is the statement that X loves pizza. Well, what's the next step? Number two is the universe or the universe of discourse. So, what is X? So, what is the universe of X here? Well, you can see in the question that we're talking about Macam 101 students here. So, maybe one guess as to what the universe might be would be that we're talking about Macam 101 students. Okay. Now, it doesn't have to be, so just keep this in mind. It doesn't have to be Macam 101 students. In fact, I'm going to do an example later on that allows us to have a different universe, but still the same logic. But for now, let's just say X is Macam 101 students. Okay. Now, the third thing we need to do is quantify it. Okay. So remember, we have open statement, we have universe, and the third, we need quantification. So are we talking about a particular Macam 101 student? Are we talking about John loves loves pizza? Or are we saying there's at least one, some Macam 101 student loves pizza? Or are we saying every Macam 101 student loves pizza? And the answer here is that we're talking about every. And the way to quantify every is that we use this notation. Okay, so this upside down A notation is talking about every. So every time you see this symbol, just read it as every. Okay, so I'm going to quantify it as such. Now, how we read this is that we read it from left to right. So I'm just going to read this quantification here. Okay, so this reads as every, or for all. Okay, so another way to say that is for all. For every x, x here is referring to the universe. So what is the universe that we're using? For every Macam 101 student. Okay, for every Macam 101 student, x loves pizza. All right, so this is exactly what we're saying in this example. So so we have the open statement, we have the universe, and we also have the quantified form. Okay, so these three things together make up one true or false statement. Okay, so let me repeat that. These three things together make up one quantified statement, which is true or false. So here you can, depending on whether it's true or not, it's assigned a true value or a false value, either a 0 or a 1. And this is how we translate every Macam 101 student loves pizza. At least this is one way to do so. All right. So now let's think. If it's true that every Macam 101 student loves pizza, then how do I prove it to you, or how do you show that that's true? Well, in a way, it's not a difficult question. We have to ask every Macam 101 student. So I have to ask, everyone out here who's watching, right? Let's call you guys X1, X2, all the way up to XN. I have to ask each and every one of you. And for this statement to be true, P of X whatever, right? Whoever you are, right? P of X whatever has to be assigned true. Now take a second just to convince yourself of that. So P of X1 has to be true. P of X2 has to be true. P of X3 has to be true, all the way up to P of Xn. So what does that sound like to you? Well, it sounds like an and, right? Because remember what we said about and? And the only way that and is false is if there's uh, at least one of the variables of the variables in the and that is false, right? So I should say that for an and to be true, everything has to be true, right? Every one of the statements in the and has to be true. Otherwise, it is false. So here, if I want to show you that every Macam 101 student loves pizza, then that means I will need to show that all of these are true. If even one of you says, no, I don't love pizza, then that's a false statement. Okay, so understand that whenever we have a for all, this is equivalent to a bunch of ands. It's equivalent to breaking the statement down into a bunch of ands involving all of the universe. Okay, all right, so let's move on to another. Oh, by the way, last thing I should mention here is to disprove a universal quantification statement, we have to find a counterexample. So let's do an example a little bit later on, but one person who doesn't love pizza is enough to say that this whole statement is false. Okay, just remember this for now. All right, so the next one that I want to talk about is called an existential quantification. Existential quantification. So in an existential quantification, this is read as some or at least one. So instead of every, this is read as some. So let's translate this statement. Some Macam 101 students love pizza. Okay, now you'll notice that it's pretty similar to how we translated the last one. So it is still about somebody loving pizza. So X loves pizza. It still could be about Macam 101 students. So the universe of X could still be Macam 101 students. Okay, but this time, instead of the upside down A, we have the backwards E. And the backwards E, once again, is read as there's at least one. Okay, now how do we read this? So the way that we read this is again from left to right. We're going to read this as there's at least one. Okay, at least one what? Well, the next one is talking about the universe. So at least one Macam 101 student X such that X loves pizza. Okay, so this is how we would read this quantified statement. There's at least one Macam 101 student. And what about this one Macam 101 student? P of X says X loves pizza. Okay, so again, I want you to verify that this is equivalent to saying there's some Macam 101 students who love pizza. And again, these three statements together, so these three parts together make up one quantified statement that is either true or false. Okay, so continuing on from what we talked about in the previous slide, uh, if I wanted to show you that an existential quantification, like some Maca 101 students love pizza, then I really need to show you that there's at least one person that is true of P of X. So again, assuming that each one of you is X1, X2, X3, all the way up to Xn, if I want to show that there's at least one Maca 101 student who loves pizza, then I need to find one of you in which when I plug your name into P, evaluates to true. Okay, so I just need to find one of you who loves pizza, right, for this statement to be true. Now, what does that sound like? That sounds like an or, right? So what we said about the or is that the only time that the or is false is if all of the inputs are false, right? All of the inputs are false. In every other case, it's true. So another way to say that is I only need to find one of you that evaluates to true for this statement to be a true statement. Okay, so now to disprove this, so the last statement here is to disprove this. For an existential quantification statement, we have to find that all items in the universe has to be false. So we have to do a little bit more work, and we have to kind of convince ourselves that every one of those statements are false, no matter what we plug in from the universe. All right, so at this point, I want you to go back and make sure that you understand the difference between universal and existential quantification and when they're used. Basically, universal is used when it's for all, when it's everything in the universe, and existential is used when we want to say at least one quantification. Okay, so let's go back for 1 second and take a look at universal quantification. So there's actually another way that we can translate this statement. So we already have P of X. Okay, so P of X we're going to import from before, right? So we still have this P of X. But now I want to add another quantification. I want to add another quantification called Q of X. And let's say Q of X is the statement X is a Macam 101 student. And instead of the universe being Macam 101 students, I'm going to make the universe of X to be all people. All people in the world, not only Macam 101 students, but all people in the world. So now the universe of X is people. Okay. Now, can we create the same logic using P and Q here that says every Macam 101 student loves pizza? Okay, so this is my goal. I want to be able to create the same logic, but this time with a different universe. And what you'll find is that there's different ways that we can express the same logic. So let's begin. I know that this statement says every, so I really have no choice but to write this. Okay, so this reads for all, but instead of for all Macam 101 students, in this case, this reads as for all people X. Okay, for all people X. What we also know is that this is somehow relating, this logic is somehow relating Q with P, right? Being a Macam 101 student with loving pizza. The question is, how are they related? Now, the short answer is that we need to find some connectives between these two. They are two expressions. So the connectives that we talked about in the last class are ands, ors, implications, or biconditionals. Okay, now just take a second just to take a guess. What do you think it is? Which one of those do you think is connecting Q with P? Now, if you're not sure, read the whole statement. Okay, so in fact, I'll read each one of those statements based on what we've done. So, are we saying that for all people X, uh, X is a Mac and one student and loves pizza? I think that one gets closest. But is it an and? Because if we say and, we mean that everyone in the world is both a Mac and 101 student and somebody who loves pizza. So, is that what we're trying to say? Well, I don't think so because it's not both. We're not saying that they're both. I'm saying that every Mac 101 student loves pizza. Okay. So what about or? Am I saying for all people, uh, those people are Mac 101 students or they love pizza? No, I don't think that's the logic either. Could it be implies? In fact, it is implies. So let me just write this in and let's read this. So now we're saying for all people, if you are a Mac 101 student, then you love pizza, right? So if you're a Mac 101 student, then you love pizza. So I think this is the same logic that's being displayed in what we're trying to represent. So typically, when we have a variable x which applies to multiple instances, we put a bracket around all of this. So once we put a bracket around all of this, we understand that x is applied to this one as well as this one. So it's the same x that we're talking about. Okay, so again, let's read it. For all people X, if you are a Mac 101 student, then you love pizza. Now, is this true? We don't know, right? We don't know if this is true, but that is the statement that's being made here. Now, just on a last note, can we say the opposite? Can we say that that uh, the universe? Sorry, for all people, if you're someone who loves pizza, then you're a Mac 101 student. And the answer is no, because we are affirming the hypothesis here. Okay, so just to let you know that the arrow does have a direction. It's not the same logic if we have the arrow going the other way. Okay, so just take a look at that and make sure you understand that. Okay, so let's move on to this one. What if I wanted to do the same thing with some Mac 101 students love pizza? So if I had X, right? Oh, sorry. Before we do that, let's add our Q of X in here. So Q of X is a Mac 101 student. And then again, our universe of X is people. So exactly the same as our last example. This time we have an exist X. So there's at least one person. Okay, there's at least one person. Okay, again, we are relating Macam 101 students with being people who love pizza. So this time, what is it? Is it an implies or is it something else? And the short answer is that this is an and. Now, first of all, let's read this and make sure that we are convinced that this is the same logic as what we had in our statement here. So this reads, there's at least one. So there's at least one person, X, in which X is a Macam 101 student and X loves pizza. There's one person like that. Okay. So I hope you can see that the logic is the same as saying some Macam 101 students love pizza, or there's at least one Macam 101 student who loves pizza. Now, some of you might be looking at this and saying, wait a minute, how come for all it's an implies and for exists it's an and? Well, because when we're talking about all, we're talking about a rule. Remember what we said about implies. Every time we talked about implies, we said it's a rule, right? It's a rule that if today is Sunday, then I go to church, right? That's a rule, right? But for some, it's not a rule. It's not an implication. In fact, if we put an implication here, right, this is automatically a true statement because we're saying if, so there is at least one that if X is a Macam 101 student, then they love pizza. Well, not everybody is a Macam 101 student. So remember what zero implies anything is. So zero implies anything is a true, right? So what you can see here is that for this statement to be true, all I need to find is one person who is not a Macam 101 student. And that would make this statement true if this was an imply. So clearly, that's not what we're trying to say. Okay, so try to convince yourself that of what I said there, but it is an and because we are looking for one particular case. We're looking for one particular Macam 101 student who is a pizza lover. Okay, so let's do one example here, just to make sure that we understand everything that we've talked about so far. So I'm just going to go to white screen, and let's do a quick example to kind of verify what we know. All right, so let's pretend that we have something like we have p of x. Okay, so the statement p of x is x squared is greater than 3. Okay, x squared is greater than 3. And our universe of x is that x is, sorry, x is an integer. Okay, now let's say that I have a statement for all x, p of x. For all x, p of x. Okay, what I want you to do, and after I give you the second question, maybe you can pause the video and work on this and see what you get. The second question I want to give you is I have p of x, and then I have x squared is less than 3. And here, the universe of x is an integer. And I want to say there's at least one x, p of x. Okay, so what I want you to do right now is take a look at these statements, translate them into proper English, and then tell me, with your understanding of math, true or false, and why. Okay, so this is very typical of a quiz question that you might get, translated into English, true or false, and then explain. Okay, now remember the explanations. So let's go through the explanations one more time. If it's a universal, if I say all p of x, then what I need to do is somehow make a statement to say that every x is true of p of x. Okay, every x is true of p of x. If I want to say for all x p of x is false, then I need to have one counterexample, one x that makes it false. On the other hand, if I want to say that for all, there exists x such that p of x, if I want to say this is true, I need to claim one case which is true. So find the one person, one Macam 101 student who loves pizza, and that's it. If it's false, if the existence is false, then I need to make a claim that there's no x that fits p of x. Okay, so I hope this is logical to you. I hope this is intuitive, but you will also need to explain what they are. Okay, so I invite you to pause the video right now, work on this, see if you get the right answer, but I'm just going to give you the answer right now. So the first statement is for all x, so all integers x, x squared is greater than 3. So is that true about all integers? Well, no, it's not, because, for example, 1 or 0 or -1 for that matter are not true. So all I need to do is give 1. Okay, so this is a false statement, false, because p of 1 is false. And that's it. That's our explanation. So here's our translation. We need false, and we also need an explanation. It doesn't have to be a long explanation. It could be a short explanation, but as long as you explain it properly, that's what the marks are for. Okay, the second question translates to at least one. There's at least one, so I'll say there's. There's at least one integer x such that x squared is less than 3. So is that true? I think so, because we can actually use the same example. It might not be always this easy, but this is a true statement. There is at least one x such that x squared is less than 3. It's true because p of 1 is true. In fact, I can say because p of 0 is true. Any of those would be a good claim. All right. Now, just while we're here, let's do a separate example. Okay, so what if I instead, let's do this in black so that we know it's a separate example. So what if I said p of x is x squared is less than 0? Okay, and I say there's at least one integer so that x squared is less than 0. So is that a true statement? The answer is no, it's not. It's a false statement because there's no such integer. So in this case, we would say false because no integer squared is less than 0. Okay, so we have to make a statement like that. So this is from our knowledge of math, obviously, but we have to claim that there's no integer squared which is less than 0, and that's how we can we can explain why this is a false statement. Okay, so again, there are a lot of practice questions in your textbook. I invite you to take a look at those and practice explaining why things are true and things are false. So in every one of these cases, we have to make an explanation as to why. All right. So at this point, I think I'm going to put another pause to the video. I'll make another stop to the video, and we're going to pick up from this point in our next video.